Hey, I'm back, and this will be the second lecture on chapter 27. And for this lecture, we want to focus a little bit more on peptides and proteins, but really talk about what they do and why they exist. And for that, we're going to look at really just one kind of example case, a very common and very important enzyme class called proteases. Right? So if I take N-methyl acetamide, just a very simple amide, and take it in water, I can hydrolyze this out to the carboxylic acid and methylamine. Methylamine. But this is an extremely slow process. It has a half-life at pH 7 or at pH, similar to your body, of about 500 years. And, if you need to repair damaged tissues or get rid of enzymes that you make and no longer need, you can't afford to sit around and wait 500 years for this thing to spontaneously fall apart. And you can extrapolate, right? All the proteins in your body are made up of amide bonds, and so they all have stability constants on the order of hundreds of years. And that's a problem. But if I look at a different amide, and I want to ask, how quickly does this particular amide hydrolyze? We can hydrolyze that amide to give like an anhydride like this. And I want to ask, how stable is this amide? It ends up having a half-life of about 8 minutes. So it's about 33 million times less stable or more quickly hydrolyzed than the simple amide above. Right? And this comes about because you are attacking this amide not with water, but rather the carboxylic acid within the same molecule. Right. So if this is not a hydrogen, if R is H, this works. If R is methyl, this doesn't work because you can't deprotonate and have it added. So intramolecular reactions are faster, but that's not really enough. They're faster, especially when the reagents are properly positioned. Okay. So if you look at this hydrolysis that I've shown you, and build a model of this carboxylic acid or this carbonyl, is located extremely close to this amide. Right? You put them both in an axial position. They're almost on top of each other. And so when you have this kind of highly organized structure, it becomes very easy for the reaction to occur. And enzymes, really take advantage of this concept. So I think it's a reasonable extension of that to say enzymes, and in this context, we're talking about proteases, which are enzymes that hydrolyze amide bonds. And I think it's fair to say that they achieve rate acceleration, at least in part, enzymes achieve rate acceleration in part by making intermolecular actions become pseudo-intramolecular. So by binding and holding reagents close together, you can induce reactions to happen that would otherwise not happen. And so we want to talk in a little bit more depth about proteases, because chemists have been really fascinated by proteases within the drug industry, right? So there are a lot of drugs that act to block protease activity. So there are antiviral systems, the HIV drug sequinavir. Is a protease inhibitor. Hepatitis C, one of the important drugs in that, is called telaprevir. And then probably the most well-known drug class, the vast majority of antibiotics are protease inhibitors. They block the function of enzymes that break apart amide bonds. And so penicillin and all of the latter-day variants thereof are all based on that model. So it's really useful to think about proteases. And we're going to talk primarily about one class called serine proteases that are maybe the most well-studied drug target enzymes. And so there are a lot of amino acids within the a serine protease enzyme, but there are three sort of essential residues that always occur near the binding pocket. Okay, so the drug, binds to an amide substrate and holds it in its pocket. And we can draw this as just a simple N-methyl aspartate for now. And within this pocket, I have a serine, I have a histidine, which has this heterocycle called an imidazole, which I will redraw with an NH bond. And then I also have an aspartic acid, which is a carboxylic acid, but at pH 7, it exists as a negative charge. And so these three residues all work in concert to make hydrolyzing this amide much better than it ordinarily would be. So in a serine protease, This serine OH is held very close to the amide bond so that it can add nucleophilically, to initiate hydrolysis and amide bond cleavage. That in and of itself is not enough. Serine is a pretty, OH is a pretty lousy nucleophile, alcohols and water. So I've got a Lewis base nearby that sort of simultaneously deprotonates the serine at the same time that I'm adding it. And so maybe it would be better to draw this arrow coming from the OH bond. But even there, histidine is a pretty lousy base, and it's really not strong enough to deprotonate serine. And so I have a third residue whose goal is really to deprotonate the histidine, which makes it which makes it more basic and allows it to deprotonate. So it's the simultaneous action of these three residues that are all held in perfect proximity that lets us add a pretty weak nucleophile in water at pH 7 to a very weak electrophile. So when I do that, I get a tetrahedral intermediate. Right? So I make the oxyanion intermediate that looks like this. So we're actually attached to the enzyme. And then we presumably need to protonate the amine to get to something that looks like that. And then now this can collapse down to kick off. And I'm left with an acetylated serine. Now the enzyme is a catalyst, so it needs to turn over. So you need to regenerate the way you started with, but that's usually not a problem. We now have an ester, and so ester hydrolysis is typically faster than amide hydrolysis. So once I get to this ester, it's fairly short-lived, and that allows me to make the parent serine, just back where we started, and then obviously we're releasing the acid. So the enzyme, probably helps with all these steps. There may be other acids that allow protonation of the amine in like this step. There probably are residues that stabilize the negative charge at this intermediate. So the enzyme does a lot of things, but a lot of the function of a serine protease can be explained just with this initial attack step. And all three of these residues are essential. Typically, if you get rid of any one of them, the whole thing falls apart and won't function anymore. So then, once you identify that a protease is important for a disease and that blocking a protease could be a useful therapeutic, we want to try to design molecules that will block enzyme function. And that has been the major way that we think about drug design for most of the last 70, 80 years, whatever it is. Clearly, it's not the only way, but it's been one of the most fruitful and dominant ways that we think about designing therapeutics. And so there's really two major classes. The first one that we want to talk about can be thought of as non-covalent inhibitors. And if we think about a non-covalent inhibitor, let's look at a reaction, some generic some generic reaction with maybe this just one intermediate, let's say, going down to product here. An enzyme catalyzes this reaction by lowering the transition state, right? So in the presence of an enzyme, your reaction might look like this. And this change in transition state energy is responsible for the faster rate of the catalyzed reaction. Right? And so within this field, we can write a postulate. Okay, so the postulate that really governs our thinking about non-covalent inhibitors is that enzymes must stabilize, and by that we could rephrase that to say form an energetically favorable interaction, or even just bind more tightly to the transition state than to either the starting material or products, right? So it doesn't do me any good if I bind the starting material really tightly and drop the energy here down here if I don't change the transition state energy. And in fact, by stabilizing the starting material, all I'm doing is kind of increasing the total energy to get over the transition state. Right? And so what we're really saying is that the largest energy difference between the catalyst bound state and the free state is going to be at the transition state. Right? That you expect this to be bigger than anything else. Okay, so that's the postulate. So what that leads us to is the conclusion that transition state mimics is that anything that looks like a transition state should bind and get stuck in the enzyme because it's going to bind more tightly than either the starting material or the product, right? And so in the case of for proteases, the transition state looks like the tetrahedral intermediate. Right, and we can really get this by Hammond's postulate. Right, so there's a fairly significant train of logic here that leads us to this conclusion. But if you accept the postulate and the conclusions that flow from it, then our goal here should be to find molecules that look like the transition state. So if we go back here, what I mean by that, this is a tetrahedral intermediate right here. And the postulate is that this looks like the transition state for this reaction. So I want molecules that look like this transition state. I can't actually use the transition state because that doesn't exist. I can't even use this tetrahedral intermediate because it'll fall apart immediately, right? So I need molecules that look like transition states, like this tetrahedral intermediate in broad strokes, but aren't. And so people have, played around and found a number of different classes of molecules that, fit that bill. So these phosphate esters, if you kind of squint, sort of look like this in the sense that they're tetrahedral and they have electronegative groups and negative charge around the 4 groups. Sulfonamides are often used as well. So we can think about simple sulfonamides, that they are often used as well as tetrahedral intermediates. Right? So we're really trying to compare these to the real substrate. Which looks something like this, right? And so all these molecules are meant to mimic that transition state. And the theory here is that if you can design something that looks enough like the transition state, it'll bind to the enzyme. But since it can't actually hydrolyze, it'll get stuck in there. And then the enzyme won't be able to bind its real substrate. So that's really the first class of inhibitors. The second class are covalent inhibitors. And these are sometimes called suicide inhibitors. And so this is really an entirely different mechanistic approach to inhibitor design. So if I think about this molecule, it looks a little bit like an amide and like a polypeptide. And so you might imagine that this thing could get stuck in the pocket next to my key serine residue that wants to be a nucleophile. And then there's a base, it's a histidine over here. And it's held in close proximity to the carbonyl, but it's also close in proximity to this alkyl chloride. And so the hope here is that in the pocket, this will deprotonate, and instead of adding to the carbonyl, it'll do an SN2. And you can appreciate that if this molecule does an SN2, we'll make something that looks like this. And at this point, the enzyme is stuck. We can rewrite that. So unlike the ester that we saw in the real case, there is now no way to regenerate the starting serine. Right, so this is not electrophilic anymore. It's just simply an ether. And O- is a lousy leaving group. And so now we are completely stuck on the substrate. And if this serine can't regenerate its OH, there's no way it can continue to do its job. And so this enzyme can sit in your body forever, but it has no way to actually do the chemistry. So electrophiles are often used, as shown here, but Um, electrophiles themselves are often too reactive or create other problems in the body, and so chemists have gotten increasingly sophisticated in how they achieve this sort of non or covalent inhibition. So another kind of substrate that we could imagine is this cyclic ester with a vinyl iodide over here. Same thing. So when this encounters a serine protease, you're going to add this thing also acts as an electrophile and adds in. And so the initial product is going to look something like this, right? But of course, this isn't a problem. This is just an ester bond, and this thing can easily hydrolyze. So this by itself doesn't cause trouble for the enzyme. The problem happens that I've now generated over here an enol, right? When this OH left, it left as an enol. And so enols, of course, tautomerize very quickly. And so when this tautomerizes to give me a ketone, we all of a sudden now expose this very good iodide leaving group. And my serine is tied up. I can't alkylate the serine, but I do have a neighboring histidine, right, which looks like this. And so the histidine nitrogen is now going to do my SN2. And so then I get something that's sort of doubly stuck to the enzyme. So I get a structure that looks like this. And you can now appreciate that we're stuck here even if the serine hydrolyzes out the ester, right? So I can cleave this bond just fine if I really want to. But again, there's no way to cleave this this new NC bond, which is just a simple alkylamine. Right? And so I basically have taken and used the serine nucleophile in the enzyme as a way to turn this sp2 iodide, which is not electrophilic because you can't do SN2 at a sp2 center. But when I hydrolyze this, now I have an sp3 carbon iodine bond, right? And so now this can be a perfectly good SN2 substrate. And so this is kind of another level of control. There's no way for this thing to act as a generic alkylating agent. It will only get activated in the active site of the enzyme. I think I've got one more example that I might as well show, and then we'll kind of wrap this up because it gets into the beta lactam class, which a lot of people know because these are penicillins and related compounds all come off of this. So this one is This is called sulbactam, at least when R equals H. This is a beta-lactam antibiotic, right? So it also hits a serine protease. This amide is the amide bond here is the major electrophilic site. And there's a lot of strain energy in a four-membered ring, so you imagine they're more reactive than a typical amide, and they do, in fact, react quite nicely to give you, out your serine adduct. I guess I could put the stereochemistry in there if you'd like. So the initial product of the hydrolysis looks like this. But now I've generated this free amine, and that free amine is a good electron donor. So this compound does not sit here, but rather it kicks off this sulfite leaving group. And so gotta be careful I save space on this page. So let's do it this way. So this becomes a sulfite leaving group, giving me a positively charged nitrogen. But then now this imine, together with the carbonyl, has made this an extremely acidic CH bond. And so the next thing that's going to happen to this compound is that I'm going to have a base that's going to deprotonate here to neutralize that charge. So that gets me to a compound which looks like that. And now what you can notice is I have very strong resonance between that nitrogen, which is a very good donor, and the carbonyl. So I can draw this highly resonance stabilized form. Which looks like this. Right? And so the strong resonance just like many other examples we've seen in this course, the resonance makes this a much less electrophilic carbonyl. And so normally, serine esters are readily hydrolyzed, and this would fall off. Right? We could imagine in a general sense that we can pretty easily hydrolyze that bond. But what we find is that in this case with sulbactam, that amide, that ester, is much more stable. And so the hydrolysis becomes slow enough that this is effectively an irreversible reaction. So even though you're making an ester, you're just making an extremely stable ester. And so this functions also as a suicide inhibitor, where it gets stuck on the enzyme and at least on a length time scale that we care about, doesn't get hydrolyzed off. So I think this kind of highlights the ways in which we can use mechanism ideas, but also structure design and reaction design to think about how molecules will interact with enzymes. So this is, we went through 3 pretty different classes of suicide type inhibitors that have all been, are all things that have been used, clinically or in medicinal chemistry concepts to try to think about how to selectively block enzymes. And so both the suicide, the covalent inhibitors and also non-covalent inhibitors are kind of actively part of how we think about inhibitor design, and how chemists have used organic chemistry concepts to solve medical problems. So I think that's really the end of what I would like to talk about from 27. There's certainly more material in that chapter, and it's also important. You should take a look at it. But for testing purposes, I would definitely focus on things within these lectures. So that's the end for this week. Next week, we're going to talk real briefly about transition metal chemistry, just a couple lectures, maybe just one, and that will wrap it up. And that'll occur after the test next weekend. So thank you very much. We are done.